In this lesson, we are comparing inductive and deductive reasoning. So first we're going to look at the definitions of these terms. Inductive reasoning means that we are drawing a conclusion based on observed patterns or trends. So for example, if we see a list of numbers and we are trying to determine what or predict what number will come next, that's generally an inductive reasoning, use of inductive reasoning. And then deductive reasoning means that we are applying previously known rules or facts to arrive at a conclusion. For example, if we have a formula, okay, something in any other kind of math where we have a formula, or even just a rule that's outside math entirely, those kinds of things are deductive reasoning. So if I know that I have a formula where every number gets multiplied by 2 and then I add 6, then I know that if I plug a 7 into that, then I'm going to multiply it by 2 and add 6 just like all the others. So that's deductive reasoning. That's where we already know the rules. And inductive means that we are just observing a pattern, so we really don't have a great way of knowing whether or not we're accurate. But for now, that doesn't really matter. We're just looking at the type. Okay, so let's look at a couple examples. For these three, we are identifying if they are examples of inductive or deductive reasoning. For the first one, it says, I've seen a stray cat in my yard each of the last 4 mornings when I leave for work. Therefore, I'll see it tomorrow morning. Okay, in this case, we have an inductive reasoning use. Okay, so this one is inductive, okay, because there's no rule that says a cat has to be in my yard, and therefore we're just using a pattern to predict that the cat will be there tomorrow. And by the way, if you want to stop the video and try a few of these on your own and then resume, that is perfectly fine. For the second example, we have an equation, f of x equals 3x minus 8. And this tells us the conclusion is that f of 5 equals 7. Okay? In this case, it is deductive reasoning because, like I said before, formulas are deductive. Here it tells us, this function here, tells us that whatever the x value is, which is what goes inside here, and this is called function notation, means that we replace every x, in this case it's the one multiplied by 3, with whatever is inside here, okay? And in this case that's a 5. So we're going to take a 5, plug it into this expression, 3x minus 8, so we would get 3 times 5 minus 8, which is 15, minus 8, which is in fact 7. So this is, now in this case we just wanted to know deductive or inductive, but we can verify that it's accurate. But this is deductive reasoning. Okay. For the third example, we have a list of numbers. This is called a sequence. When we have numbers that are listed, whether or not there's a pattern, it's called a sequence. And it's our pattern is 3, 6, 12, 24, 48, and we are looking for the next number to be, sorry, one second. Okay, we're looking for the next number to be 96. In this case, there's no rule that tells us the relationship between each number and its previous numbers, so the reasoning here is going to be inductive. Okay? Oh, there we go. Inductive, but let's go ahead and check that that is the correct conclusion, okay? So looking for a pattern, I see that between 3 and 6, we could look at it as adding 3 or multiplying by 2. In this case, when we go to the next pair of numbers from 6 to 12, adding 3 doesn't work anymore, so I'm going to try multiplying by 2 and see if that's consistent, okay? And then from 12 to 24, yep, multiplying by 2. 24 to 48, again, multiplying by 2. So it does make sense, based on inductive reasoning, that the next one will be 96. Okay, we've got another term here that has some other terms within it. Logical arguments are statements that include a premise or possibly more than one premise and a conclusion, okay? So these are all examples of logical arguments. Generally, we start with some kind of hypothetical statement. Sometimes these are called conditional statements. So this first statement right here is a conditional statement because it says if something, then something else. So here, if it storms, then all soccer games will be canceled. Okay, so that's a conditional statement because within it, it has a hypothesis, which would be the storming. Okay, I'm going to abbreviate there. And a conclusion, all soccer games will be canceled. So we have a hypothesis and a conclusion within that statement, okay? But that whole statement itself is one of the premises of the logical argument, okay? And then we have another statement that takes this from a conditional, a hypothetical, to something that's actually happening. And here it says, it is currently storming. So now the hypothesis of, there we go, the hypothesis of the previous conditional statement has happened. So it takes it from a possibility to something actually happening. And because of the conditional statement, we have to reach the conclusion that the soccer game will be canceled. Okay? So we have to reach this conclusion. All of these statements together represent a logical argument. The first two statements are considered premises. Okay? And then we have our conclusion down here. And if we think about whether or not this is an example of inductive or deductive reasoning, this one is going to be deductive because we start with an actual rule. There is a rule that if it storms, soccer games will be canceled, okay? And then we apply that rule when it storms. So this is also deductive reasoning. Okay? We have another example here of a logical argument. One second here. There we go. Sorry, little technical glitch here. Okay, so this is what we're looking at now. We have a statement that says the area of a square is the square of its side length. Okay? So again, this is a conditional statement. It doesn't say that there is a square in existence somewhere, but if we have a square, then its area is found by squaring its side length. And I know I'm using square there twice, but this square is the shape, okay? And this one as in multiplying it by itself, okay? It is a conditional statement. It's not written as an if-then statement. Sometimes it is helpful to rephrase a sentence as if something, then something else, because then when we're looking for the logical arguments, we can identify the hypothesis and the conclusion. In this case, if I wanted to write this as an if-then statement, okay, I would probably identify my hypothesis as the existence of a square and the conclusion as its area is the side length squared, okay? So I might say, I might say, if I have a square, okay, then, conclusion, its area is the square of its side length. Okay, and so I have a square is the way that I worded the hypothesis. The wording doesn't have to be exactly that. We could say if figure A is a square, or if Robin is a square, or anything. If we have a square in our hypothesis, then the area of that square is the square of its side length. Okay, so then that's the conditional. That's one of the premises. And then we have another premise right here that says a square has a side length of 9 centimeters. So now we've taken the previous statement from a hypothetical, and there is an example of where the hypothesis comes true, okay, where we do have a square. And so we have to conclude, based on the first premise, that its area is the square of its side length, and 9 squared is 81, so that is how we get this conclusion right here. Okay? All right, last examples here. We are going to use inductive reasoning to predict the next entry. Here we have some lists of terms, some sequences. Looks like most of them are numbers except for one that has some letters in there. So when we are looking for patterns, Some of the things that we should consider are what is the difference between each term and its previous term. So are we adding the same amount every time? Are we adding numbers that may not be the same every time but that proceed in a pattern? For example, maybe add 1 the first time, add 2 the second time, add 3 the third time. Are we multiplying by the same number between each pair? So maybe times 2, times 2, times 2, times 2, something like that. Those are common patterns. Also, some things to consider would be, do we have the squares of numbers or the cubes of numbers? So am I looking at a list of 1 squared, 2 squared, 3 squared, 4 squared, or 1 cubed, 2 cubed, 3 cubed, 4 cubed, etc. So sometimes it takes a little bit of guessing and checking or playing with the numbers to figure out what the pattern is. But if in a question like this where it says use inductive reasoning to predict, then there is some pattern present. So might take a little bit of a try, but we should be able to get there. Okay, so for the first one, nothing jumps out to me right away. So I'm going to look at the difference between each subsequent number and its previous number. Okay, so looking at this first one, from 15 to 8, I can see that we have subtracted 7. Okay, and then from 8 to 1, we've subtracted 7 again. Okay, so because it was the same number both times, then my early prediction is that I'm going to continue subtracting 7. I do need to keep checking. Just because a pattern holds true for the first 2 numbers does not mean that it's going to hold true for the rest of the sequence. Okay, so I check again from 1 to -6. Again, we've subtracted 7. And verify it with the last one, subtract 7 again. So then the next number in the sequence is going to be -13, and I need to subtract 7 again, and that gets me to -20. All right. For part B, I don't have numbers, but I'm looking for a pattern based on those letters. They're definitely not just a list of letters alphabetically, okay? But if I think about this a little bit, I think that maybe the J, F, M, A, M are representing maybe the initials for a common sequence. In this case, I would try maybe days of the week or months, or maybe alphabetical, like the spelled out words for numbers, like O for 1, T for 2, T for 3, F for 4, something like that. In this case, it is. It appears to be. I can't say for sure because I'm predicting, but it appears to be the first letters in the month starting with January. So it looks like this is January, February, March, April, May. So according to that pattern, the next term or the next month would be June. So it looks like my next letter is going to be a J. So my prediction is J. All right, for part C, back to numbers. I'm going to, like I usually do, I'm going to start with a difference. And I see that from 2 to 8, we're adding 6. Okay? And then from 8 to 18, we're not adding 6. We're actually adding 10. Okay? So at this point, I can continue with the addition and looking at the difference there and hope that maybe I get a pattern in the numbers that are being added, okay? Or I could try something else. If I try multiplication, from 2 to 8, I get times 4. But then from 8 to 18, now I'm not even multiplying by a whole number. It looks like I'm multiplying by 2, but that only gets me to 16. So I need another. So this looks like it's times 2.25. Sorry, it's kind of small there. Hope you can read it. But it's definitely not a 4. Okay, so I'm going to go back to the addition and see what happens after adding 10. So from 18 to 32, I am adding 14. Okay, and then from 32 to 50, I am adding 18. And if I consider the numbers that were added, I've got 6, 10, 14, 18. There appears to be a pattern there where each time I add the next, the number that is 4 more than the previous difference. So if I'm following that pattern, then it appears that I should add 22 for the next number, which gets me 50 plus 72. I'm sorry, 50 plus 22 gets me to 72. Okay? Now this one right here, there's actually a second pattern that would still get us to 72. Another thing that I notice, because I'm not adding the same number every time, is that I should maybe check some powers of numbers. I mentioned this before, like maybe squares or cubes of numbers. In this case, it's not exactly a list of squares, but I do notice that my numbers are 2 times 1 squared, and then 2 times 2 squared, and then 2 times 3 squared. And so I also have this pattern where I am doubling the next square number, okay? And then 2 times 5 squared. So it would make sense that my next number is 2 times 6 squared, which is 2 times 36, which is 72. So that gets us to the same place. So it's just another pattern. Like I said before, sometimes it just takes practice with these and some guessing and checking until you find a pattern that works consistently. Okay? This last example, I have 5 fractions, and if I look at them as fractions first, there's nothing, like a whole fraction itself, there's nothing that really jumps out. I could change them all to decimals. 2/5 is the same thing as 0.4, but then it gets kind of gross really quickly. 3/7, I don't have that one memorized. I'm not sure what that is off the top of my head. 4/9 is 0.444. 5/11 is, and we have an issue where we're just getting some not very attractive looking decimals. So instead of that, what I'm going to do with these fractions is consider the numerator and denominator separately, okay? If I do that, looking at my numerator, let me give myself a little more room here. Uh-oh, should have done that. Okay, 1 second. Yeah, sorry, fix the rest of it later. Okay. So I see in my numerator that I am adding 1, and then adding 1, and then adding 1. So I have this pattern where the numerator is increasing by 1 each time. So following that, I should have 1 more. My next numerator should be a 7. And then for the denominator, again, I can see that these have a common difference. This is +2, +2, etc., all the way across, +2, +2. So 13 + 2, my next denominator should be 15. Okay? So according to the pattern where the numerator and denominator are really, the patterns are defined separately, we end up with 7/15.